Section: Introduction. We are diving into the exciting realm of artificial intelligence and its potential to outperform in strategic reasoning games like chess, Go, poker, and even diplomacy. Now, while these AI models are indeed sophisticated, they face a significant roadblock. They struggle to adapt to unfamiliar strategic situations because their training is generally confined to a specific game. In contrast, humans can nimbly adapt to a wide variety of situations, such as new rules, different styles of play, or even unusual winning conditions. This is the challenge we aim to tackle in our study. How can we improve AI algorithms to think strategically and flexibly, akin to a human? We're interested in their ability to anticipate possible moves from opponents, who may have different goals, and formulate the best strategy accordingly. This line of thinking is a cornerstone of game theory, where multiple participants might have contrasting interests. Recent studies indicate that large language models, LLMs, trained on diverse data sources, show promise in this regard. They demonstrate a potential to understand complex and context-specific information and adapt to various tasks and environments. But there's a catch. These LLMs can sometimes be shaky and inconsistent, especially when it comes to understanding social situations and strategic planning. To make these models more robust and dependable, we've come up with a unique approach. We'll provide them with examples of strategic reasoning, teaching them to navigate through different situations, gauge the effects of their actions, and develop beliefs. With this method, we expect LLMs to apply these lessons to unfamiliar scenarios. So, what does it take for an AI agent to reason strategically like a human? 3 key things. 1. Navigating through possible states and actions. Let's consider a bot negotiating with a vendor. It needs to comprehend the spectrum of available inventory and how its offers impact the negotiation. 2. Assigning values to states and actions. Our bot needs to understand what is valuable to both itself and the vendor. 3. Formulating beliefs based on limited information. It needs to interpret the vendor's behavior and deduce the value they place on items. To enable this, we've created an automated prompt compiler that generates examples of strategic reasoning. This tool structures reasoning prompts, nudging the LLM towards more flexible thinking before making a decision. The rest of our study is laid out as follows. First, we introduce our approach for systematically generating strategic reasoning prompts with our prompt compiler. We then put this to the test with matrix games and negotiation games, using a mix of new game structures, different objectives, limited information, and communication. Our goal here is to highlight the model's ability to navigate, assign values, and form beliefs in unfamiliar contexts. We finally apply our approach to a realistic negotiation task, and voila! We have a negotiation agent that talks and reasons like a human, without any prior training. We believe our results strongly showcase the potential of language models for flexible strategic reasoning, with the added ability to adapt to new situations with minimal or even no additional examples. Section Summary. The paper explores the potential of language models to engage in strategic reasoning and address the limitation of existing AI algorithms in their ability to adapt to new contexts. Large language models, LLMs, have been shown to express human-like strategies and flexibility in reasoning, but can be unreliable in their reasoning. The authors propose an approach that shows models how to search through states, evaluate actions and their effects, and form beliefs by using systematically generated demonstrations of strategic reasoning, which can enable LLMs to reason strategically, flexibly, and reliably. Section: Related work. In this section, we delve into 2 significant fields of study: the evolution of strategic thinking within AI entities, particularly in game-based settings, and the development of reasoning abilities within large language models, LLMs. Firstly, let's consider the strategic thinking within AI entities. This area has seen substantial progress, particularly with advancements in game-playing AI. This progress has been catalyzed by leaps in reinforcement learning and self-play methodologies, along with their incorporation into tree search techniques. This has paved the way for the development of successful strategic AI agents capable of competing in games such as chess, Go, StarCraft, poker, and Dota. What these methodologies demonstrated was the powerful capacity of self-play and reinforcement learning to formulate strategies that can surpass human players. Nevertheless, these techniques encountered limitations, especially when it came to creating AI agents proficient in adapting to new and unexpected scenarios, such as changes in game rules or objectives. Notably, Cicero demonstrated how LLMs could be employed to create adaptable agents. These agents can interact and negotiate with humans through dialogue by merging strategic reasoning and language modeling techniques. This innovative approach led to the development of a dialogue-based agent skilled in the game of diplomacy. However, even with this successful implementation, Cicero's approach had its constraints. They used a separate strategic planner and relegated the LLM to translating predictions into dialogue and some level of implicit planning. This resulted in a less flexible agent that would require retraining to adapt to a new game variant or rule changes. As a response to this limitation, our study seeks to explore methods of directing the language model through systematic prompts to create a more adaptable strategic planner. Secondly, let's focus on reasoning with LLMs. LLMs have proven to be effective at reasoning across various contexts, particularly when combined with prompting techniques that enable them to process their actions. Other methods have further enhanced reasoning abilities by compartmentalizing problem-solving steps, linking language models as modules or cascades, refining the model's reasoning through fine-tuning or bootstrapping, and by tuning through human feedback. Despite these successes, LLMs have demonstrated limitations in reasoning about agents. Furthermore, there have been limited attempts to leverage these models for complex strategic reasoning tasks. In this study, we aim to address this gap. We build on these advancements to boost the reasoning capabilities of LLMs and devise a systematic prompting technique to make them adaptable and reliable strategic agents. Section Summary. The section discusses two areas of literature: the progress of strategic reasoning with AI agents in game-playing environments and the advancement of reasoning capabilities in LLMs. While game-playing AI has shown success in creating policies that outperform humans, they are limited in adapting to novel situations. On the other hand, LLMs have been successful in reasoning in various contexts, but are limited in their reasoning about agents. The paper explores how to guide LLMs through systematic prompts to make them flexible and reliable strategic agents. Section: Strategic Reasoning with Language Models. Our goal is to enhance the strategic decision-making abilities of language models, making them more reliable and adaptable across different situations. We do this by systematically creating prompts that embody common strategic reasoning strategies, specifically focusing on search techniques, value assignment, and belief tracking. To help understand our methods and strategies, let's explore two types of game settings we're studying: matrix games and negotiation games. We can illustrate these games using the structure of a multi-agent Markov decision process, or MDP. In a game with n participants, we represent the set of all possible states of the world as S, and the actions that each player can take as A. We denote the rewards as R, and the transition probability matrix, which defines how the state of the world evolves as players take actions, as P. However, in situations where not all details of the state or the rewards are visible to all players, we call this a partially observable setting. Matrix games. Matrix games are simple games devised by game theorists that highlight rational strategic behavior. Players in these games aim to maximize their own gains while being fully aware of the strategies of others. These games have influenced a wide range of fields, from economics and politics to evolutionary biology. In matrix games, the range of possible states, actions, and rewards depends on the dimensions and values of the payoff matrix. For example, a 2x2 matrix game has 2 players, and each player has 2 possible actions. We add complexity to these games by altering the rewards, players' objectives, action space, the number of players, the visibility of the game, and by adding multiple rounds to a game. Negotiation games. In a negotiation setting, we use a game known as Deal or No Deal. This game involves 2 players who have to divide 3 types of items, hats, books, and balls, among themselves. The players each assign different values to these items and do not know how the other player values them. Across different rounds, we vary the number of each item and the player's individual valuations for these items. Section Summary. The authors propose a method to guide language models towards better strategic reasoning and enable them to generalize reliably to new domains. They provide a systematic approach for generating prompts that incorporate structure based on common strategic reasoning techniques, such as search, value assignment, and belief tracking. They demonstrate their approach and prompting strategies using 2 game settings: matrix games and negotiation games. Section: Incorporating structure in strategic reasoning prompts. To improve the performance of large language models in strategic reasoning games, and to enable them to tackle new scenarios, we introduce an in-context learning method. We demonstrate this approach by offering examples of how to solve strategic games. Our key realization is that the demonstrations we provide must include structural elements for reasoning about strategic games. Such elements facilitate the use of cognitive tools vital for strategic reasoning, like search, value assignment, and belief modeling. To illustrate this, we employ a prompt compiler. This tool uses a given game as an example and generates an instance of strategic reasoning. The compiler breaks down this instance into elements of search, value assignment, and belief tracking. In matrix games, our generated examples come from simple and restricted games. This method enables us to systematically test the model's ability to generalize to new scenarios. Meanwhile, in the negotiation domain, the demonstrations are provided by a human player. An expert demonstrator annotates these human demonstrations with reasoning steps tied to search, value assignment, and belief tracking. We use these annotations in the compiler in both settings, utilizing the broken down games as context to guide the language model's behavior in a new strategic game. Let's imagine a scenario where a player doesn't know whether the state of the world is hearts or spades. In this case, we demonstrate how to break down reasoning into search, value assignment, and belief formation to figure out the best response. A crucial element of our strategy is search. This ability to search flexibly is vital for adapting to changes in game aspects, like the rules, the number of players, or the action space. Whenever feasible, we conduct a comprehensive search by examining all possible outcomes. In the game's decision tree. For instance, in a matrix game, a player needs to consider the other player's actions to find the right states to evaluate. We generate prompts that illustrate this searching process. An important part of searching depends on understanding the opponent's potential actions, specifically, the layers of recursive thinking that a player undertakes about other players' moves. For example, a beginner player, who doesn't consider what other players are thinking, only explores the rewards obtained for their actions. On the other hand, a player employing a higher level of reasoning first imagines the actions the other player might take and then evaluates their own options to choose the best response. As games get more complicated, the larger decision trees and more extensive rule sets can exceed the language model's context window, leading to less reliable reasoning. To handle this, we recommend dividing the reasoning process into two tools: search and calculate. The search tool allows the model to examine subtrees of a game iteratively, while calculate lets the model perform simple operations, such as calculating an average or determining the maximum value. Our approach can enhance a language model's ability to manage complex games by enabling modular, effective search and reasoning. When it's not feasible to search exhaustively, we conduct search through a cycle of proposing and refining candidate actions. We propose an action, evaluate it, and revise it to generate a better action. We repeat this process a certain number of times, as shown in the demonstrations. Each step might look something like: try 1 of n. If we choose action A, the expected reward would be R1. This is low, so we can try again. Try 2 of n. We revise our action to action B. The reward would now be R2, and so on. Our next strategy involves value assignment. Understanding values flexibly is essential to generalize to new objectives. We alternate between searching and assigning values for each state action pair. We offer natural language explanations to help the model understand how these values are calculated. Lastly, we employ belief tracking. We estimate hidden information, such as player values or unseen states, by searching through the possible space of hidden information and keeping track of evidence across multiple interactions. For instance, if a player's rewards are hidden, we observe their actions to estimate what their rewards might be. An example belief might be: the player chose the book over the balls 9 out of 10 times, so they probably prefer books. Section summary. The paper proposes an in-context learning approach to enable large language models to solve strategic reasoning games and generalize to new instances. The proposed approach incorporates structure in the prompt to enable LLMs to leverage cognitive tools useful for strategic reasoning such as search, value assignment, and belief modeling. The prompt. Compiler takes an example game and automatically generates an example of strategic reasoning, which is decomposed into components for search, value assignment, and belief tracking. Section. Experiments. We've carried out various experiments to highlight the effectiveness of our prompting approach, focusing on the adaptability and consistency offered by its 3 key elements: search, value assignment, and belief modeling. You can find all the prompts and evaluations we used on our project website. For these experiments, we used several language models. One of these models is code-specific, namely Code DaVinci 002, Codex, and the other 3 are text-based models: Curie 001, DaVinci 002, and DaVinci 003. We selected the most predictable output from the language model, with no randomness, termed a temperature of 0. During the reasoning phase, we let the language model make selections without any restrictions. However, when it generates a stop phrase, signified by agent action, we limit the agent's action space to only valid actions, which is facilitated by a tool called Synchromesh. We've also transformed the game structure and rules into text for the language model to understand. To put our approach to the test, we've included several baselines for comparison. These include 1. A no training and a limited training baseline, where the model predicts the action without using a scratchpad or sequential reasoning. 2. a no training sequential reasoning baseline, given. An instruction to, let's think step by step. 3. Variations where we only use specific parts of our strategic prompts, either the search, the value assignment, or both, but without the belief modeling. We assess the performance of our approach by measuring how accurately it chooses the best response. Section summary. The experiments conducted in this study demonstrate the effectiveness of the prompting strategy, which consists of search, value assignment, and belief modeling components. The language models used include a code-based model and 3 text-based models, with the most deterministic setting being used for sampling. Baselines were also included, and performance was measured by accuracy in choosing the best response. Section. Searching with language. In this section, we'll be discussing how we have applied language models guided by demonstrations from our method to solve unfamiliar game trees. The aim is to make the model adapt to new rules, rewards, and structures reliably. The first area we'll look at is matrix games with new reward schemes. We have designed an experiment to test the model's ability to generalize to different reward structures across various game formats. These formats include sequential games, simultaneous games, and complex formats that involve both sequential and simultaneous play. In these games, players aim to maximize their rewards by choosing the best possible actions, either at the same time, simultaneously, or one after the other, sequentially. For this experiment, we've set up the model to play against a simple, inexperienced player, which we refer to as a LEVEL0 player. To assess the language models, we used straightforward 2x2 matrix games, focusing on single-stage simultaneous or sequential games and 2-stage games. To instill strategic thinking in the models, we provided them with examples of 2 fundamental matrix games in the correct format. In the first game, the rewards for all actions consistently decrease, from 8 to 1. In the second game, we showcased a game where there are equal payoffs or ties in rewards, aligning with the structure of the main evaluation game, be it simultaneous or sequential. While these examples maintain the same game structure, they utilize simpler strategies compared to the main evaluation game, thereby helping to develop strategic reasoning in the model before the primary evaluation. We tested the model's adaptability to new rewards on various versions of matrix games. For single-stage games, we chose 7 types of games: Prisoner's Dilemma, Chicken, Stag Hunt, Battle of the Sexes, Market Entry, Imbalanced Matching Pennies, Deadlock, with 5 different reward variations each, totaling 35 games. The games require a range of successful behaviors, including cooperation, compromise, and antagonistic action. For 2-stage games, we used 2 game trees, one with simultaneous actions followed by sequential ones, and the other in the opposite order, with 15 different reward variations, totaling 30 games. This diverse range of games allowed us to evaluate the model's ability to display different strategic behaviors. The results showed that language models prompted to systematically search and assign values using our method successfully adapted to new reward schemes. Depending on the given rewards, the models were capable of expressing various behaviors. However, simpler prompting strategies such as zero-shot, two-shot, and zero-shot caught prompts were less successful in adapting to new rewards. Moreover, when we removed some parts of the search or value assignment from the strategic prompt as part of an ablation study, the model's performance became less reliable. This revealed the importance of parts of our reasoning structure in making the language models more reliable. Section summary. The section discusses how language models can learn to solve novel game trees by being guided with demonstrations generated from a specific method. The models are tested on different variations of matrix games, including single-stage and 2-stage games, to evaluate their ability to show different strategic behaviors. The results show that the language models prompted with a specific method generalize successfully to new payoffs and are more reliable than vanilla strategies of prompting. Section. Complex game structures, factoring strategic reasoning. In this experiment, we want to see how language models handle more complex strategic reasoning scenarios. Specifically, we're looking at matrix games that have a lot more going on without providing additional contextual examples. There are 2 main ways we're upping the difficulty. First, we're introducing bigger action spaces. We've looked at games that have 3x3, 4x3, 5x5, and 6x6 action matrices. See our supplementary figure for more. It's a challenge to model and find the best strategies as the action space expands. Second, we're adding more players into the mix. We test 3, 4, and 5-player games. These games come with a host of challenges, like the formation of alliances, competition, and group social dilemmas. These scenarios demand a higher level of thinking about the interactions and influences between players. The games are essentially scaled-up versions of the 2x2 games, with payoffs adjusted to match. As examples, we use a 3-player prisoner's dilemma and chicken game to see if the models can handle games with more players. Here's the catch, though. We're still only showing the model 2 basic examples of how to solve 2x2 matrix games. It then needs to apply what it's learned to these entirely new game structures and rewards without any prior exposure, a process we refer to as zero-shot generalization. Our findings show that as we make the games larger, the language model starts to struggle, mainly because it has a limited context size. Refer to our figure for more. But this problem disappears when we use what we call factored search and reasoning, which helps the model generalize perfectly to the new, more complex games. We also found that when the models can reason based on the provided examples, they're more adaptable. They can handle games with more players and actions, even without examples of these new game structures. This is an encouraging finding, suggesting that the use of factoring allows us to handle much more intricate games. We also explore how factoring could potentially be applied to repeated strategic reasoning in a later section. Section Summary. The study evaluates the strategic reasoning of language models on matrix games with increased complexity, including larger action spaces and more players. As the size of the games increases, the language model struggles to keep up with the complexity due to its limited context size. However, factored search and reasoning allow the model to generalize to new games perfectly, demonstrating the potential for factoring to be used for iterated strategic reasoning. Section. Assigning values with language. In this section, we'll discuss how our evaluation method of states and actions through language can enhance the versatility of large language models, or LLMs, enabling them to learn and adapt to new objectives. We'll begin by demonstrating how our method can be applied to a new objective without requiring any extra examples. We'll then discuss how demonstrations can effectively teach the model to optimize for a fresh objective in a real world context. Our study includes a variety of objectives in a set of matrix games. These scenarios cover 4 main objectives that the players strive for. 1. The first scenario involves a player trying to increase their own reward, knowing that their opponent aims to assist them. 2. The second scenario involves a player attempting to assist their opponent in maximizing their reward, with the understanding that their opponent also seeks to maximize their reward. 3. The third scenario sees both players trying to maximize their collective welfare. 4. Lastly, in the fourth scenario, the players aim to maximize a unique reward, called daxity, defined as the advantage, or the difference between their own reward and their opponent's reward. Throughout these scenarios, we maintain consistent demonstrations, as in the earlier mentioned section, where the goal of the players is to maximize their rewards. It's crucial for the model to adapt to these new objectives in a zero-shot manner, which means that the model only gets to see demonstrations of players maximizing their rewards, along with an instruction outlining the new objective. In our findings, we discovered that our reasoning structure, coupled with a step-by-step process for inferring values and search techniques, is effective in generalizing to alternate objectives. This proves that language models can indeed be leveraged as a robust tool for optimizing a variety of new objectives. By demonstrating the ability to generalize to new objectives without the need for retraining, we provide evidence that LLMs can be optimized not just for a specific reward signal but also for abstract goals. A significant characteristic of human-level reasoning is the capacity to chase new goals without compromising proficiency. The ability of LLMs to demonstrate this trait when prompted strategically is a positive indicator. It suggests that with the right prompts, LLMs can exhibit flexible strategic reasoning. Section Summary. The method for evaluating states and actions in language can help large language models, LLMs, learn new objectives and generalize to them without additional examples. The model can optimize for new objectives in a zero-shot manner, using the same demonstrations as before and an instruction describing the new objective. The results show that LLMs can optimize for abstract goals and pursue new objectives without losing competency, which is a promising sign for adaptable strategic reasoning. Section. Model as a fair broker. Our focus here is on the role of a model acting as a fair broker. Let's dive into the setup of our experiment. In this experiment, we imagine a realistic negotiation scenario where our model works as a broker. Its role is to balance a range of fairness objectives in order to land on a successful deal. To put our model to the test, we use the deal or no deal dataset. As a broker, the model has full insight into each player's values. It's then tasked with proposing a deal that aligns with a certain fairness standard. What makes this challenging is the intricate nature of the action space when dividing the prize pool, given that it would be practically impossible to examine all possibilities exhaustively. Moreover, the model has to adjust to ever-changing fairness objectives. We focus on 2 main objectives that our broker model has to work towards. The first objective is equality, which implies minimizing the discrepancy in the values received by the players. The second objective, known as Rawlsian fairness, is about maximizing the lowest value that's offered. We assess how well our model performs by measuring the discrepancy between the fairness of the proposed deal and the optimal deal. The model is trained to optimize these objectives via a technique known as few-shot learning, using a handful of demonstration episodes. We provide 5 episodes that show the model how to optimize a goal and teach it the process of proposing an action, evaluating it, and revising it. We then test its ability to generalize these skills to 100 new deals. To measure the performance of our model, we compare the value of its proposed deal to the highest possible value. To evaluate our model, we use 100 negotiation contexts from the deal or no deal dataset. Now, let's discuss the results. We observe that the model's ability to iterate reasoning processes allows it to propose fairer deals compared to a model lacking this ability, effectively cutting the error rate by more than half. This underscores the significance of iterative reasoning for negotiation models in order to achieve optimized solutions in complex search problems and value assignments. Section Summary. In this section, we test a negotiation game where the model acts as a broker and optimizes fairness objectives for a successful deal. The model learns to optimize equality and Rawlsian fairness objectives through few-shot demonstrations and is tested on 100 new deals. Results show that the iterated structure of reasoning enables the model to find more fair deals, indicating the importance of iterative reasoning for negotiation models to converge on optimized solutions in complex search and value assignment problems. Section. Forming beliefs with language. Understanding beliefs through language. We demonstrate how language learning models, LLMs, guided by our method to keep track of beliefs, are able to solve games with different types of partially observable information, such as hidden states, truthfulness of communication, and values of the opponent. Discussing beliefs about states. Setting up the experiment. In this part of the study, we introduce the concept of partial visibility in the world state. We analyze a sequential game where the player, in this case, the model, cannot fully see the world state. However, they can observe the actions taken by their opponent and the rewards they receive for different world states. Therefore, the player can note the opponent's actions and values and must form a belief about the world state based on these observations. We examine 3 different types of game trees, refer to fig, front, to illustrate how language can be used to form beliefs about hidden information. The structure of the prompts used can also be seen in fig, front. Their performance is assessed based on their ability to choose the best response, which is the response that results in the highest payoff. To illustrate reasoning about hidden world states, we use 2 examples of games with minimal rewards, similar to those discussed in previous sections. We test generalization with 3 game structures and 5 variations of payoffs. The first game structure is the same as the one used in the contextual demonstrations but with significant payoffs. In the second structure, the world has 3 hidden states instead of just 2. For the final structure, the number of actions that the opponent can perform increases from 2 to 3. The findings. Our results show that models guided by our structures of reasoning significantly outperform the basic models, proving capable of generalizing to new structures, referred to tab, Bell. This demonstrates how language can enable models to reason in situations of uncertainty and limited visibility, which is a crucial skill for strategic reasoning and interaction. The ability to form beliefs and reason under partial visibility implies that language models can comprehend situations where information is not perfect and can make inferences from limited cues. This kind of flexible reasoning is vital for interaction in complex, strategic environments. Our method showcases one way to impart this capability by using natural language to guide a model's exploration over possible hidden states. Another example of how language can be used to form beliefs about hidden information based on limited signals is by reasoning over the honesty of an opponent's communication, as discussed in ASIC, Truth. Section Summary. The section discusses how language can be used to form beliefs about hidden information in partially observable games. The authors introduce partial observability in the state of the world and show how language can be used to form beliefs about hidden information. They evaluate the performance of their method and demonstrate how language enables models to reason under uncertainty and limited observability, a key capability for strategic reasoning and interaction. Section. Realistic scenario. Model as a negotiator. We want to explore the possibilities of creating a negotiation bot that behaves like a human without the need for any additional training. To do this, our experiment involved the bot forming an understanding of human values through several rounds of interaction. To test our approach, we used the deal or no deal environment, limiting the negotiation process to 3 turns or 6 offers. The process begins with a human proposing an offer, after which the bot can either propose a counteroffer, or accept or reject the deal. If the bot rejects an offer, no reward is earned. To guide our bot, we provided demonstrations from a highly skilled human player who played against another human. These demonstrations were then systematically annotated to create 7 demonstrations, giving the bot a model to follow. We then tested the bot with new negotiation partners, each with different values and quantities of items. We compared our bot's performance to 2 other models, one that didn't employ a chain of thought prompting method, and another that used strategic reasoning but didn't form beliefs about the other player's values. To evaluate our methods, we conducted a study with 11 human participants. They interacted with the 3 different negotiation methods for 3 rounds each. Afterwards, the participants were asked to rate each method in terms of human likeness, reasonableness, aggressiveness, and willingness to compromise. The results were promising. Our approach outperformed the other models in numerous areas, securing a higher average reward. Notably, the humans also earned slightly higher rewards when negotiating with our bot. Our bot didn't require any additional training and successfully mimicked the style of the human player in the demonstrations. This success was also evident in the post-study survey, where our bot was rated as being more human-like, reasonable, and willing to compromise, and less aggressive. These results show that our method of prompting a bot to use strategic reasoning in language can help it handle complex tasks like negotiation without needing large training datasets. This type of bot could potentially have long, open interactions with humans, and may even perform at a human level in social and strategic tasks. It's an exciting first step towards AI agents collaborating with and assisting humans in innovative ways. Section Summary. The authors demonstrate how they can create a human-like negotiation bot without retraining in a realistic negotiation setting by forming a belief over a human's values through multiple rounds of interaction. They evaluate the model on new negotiating partners in settings with new values and item quantities and show that their method outperforms baselines on multiple metrics, achieving a higher average reward and consistently rated to be more human-like, reasonable, compromising, and less aggressive. This shows how their method of prompting a model to reason strategically in language can enable agents to handle complex, real-world tasks, like negotiation, without requiring large training datasets. Section. Discussion. We embarked on a journey to illustrate how language models could be trained to think strategically about other participants using a carefully crafted prompt. This prompt incorporated elements of search, value assignment, and belief tracking strategies. Our approach allowed these language models to adjust to new strategic settings that were presented with new rules, different game structures, unfamiliar goals, and the necessity to form beliefs based on undisclosed information. This knowledge led us to create a model that could negotiate with humans in a thoughtful and human-like manner, all while trying to maximize utility or benefit. However, we encountered several obstacles when applying language models to these areas. For instance, intricate games may necessitate more demonstrations and instructions for the language model to comprehend the rules and behavior specific to each game. In these situations, our capabilities are restricted by the language model's context length. While we could utilize language models based on retrieval for this purpose, expanding these models isn't a straightforward task. Additionally, complex games often demand thinking over a longer duration, meaning more turns than what we initially considered, leading to much longer chains of reasoning where the performance of the language model might deteriorate. Despite these challenges, our tests on the factored modeling approach were promising. Other training methods could further aid the model in quickly adapting to a new task, all while maintaining flexibility by using language as a way to think. For example, we could refine the model's performance by supervising fine-tuning over reasoning trajectories, employing rewards as a means to enhance the model's performance, or leveraging successful trajectories to bootstrap reasoning. Although we didn't focus on identifying equilibria, which are stable states in a game where no player is motivated to alter their strategy, the search and best response tactics we suggested could potentially be expanded to allow for level K reasoning, a process that eventually leads to equilibrium. A simple expansion of our factoring approach could implement this kind of recursive reasoning. We're optimistic that our findings will spur additional research into the use of language models for reasoning in complicated multi-agent settings, like the games Diplomacy and Hanabi, rather than being limited to dialogue only. Our method also holds promise for simulating human-like behavior, which could lay the foundation for more realistic designs of economic policies, such as agent-based models of markets with human-like agents. These models could help simulate social conventions and individual models of desires and beliefs, leading to more accurate simulations of complex social interactions. We hope our research encourages further exploration into how language models can be used for reasoning in these types of environments. Section Summary. The paper demonstrates how language models can reason strategically about other agents using a structured prompt based on search, value assignment, and belief tracking strategies. However, challenges arise in using language. Models for complex games, which require longer reasoning traces and more demonstrations to understand the rules and game-specific behaviors. The authors hope their research will inspire further exploration into the use of language models for reasoning in complex multi-agent settings beyond dialogue and for modeling human-like behavior in economic policy design.